This video is about the Henderson Hasselbalch equation. And so we're going to start by writing out an equation for an acid ionization. And then we can find we can write out the equilibrium expression. Now I'm going to rearrange this to solve for the concentration of hydronium. And so that's going to be Ka times the concentration of Ha over the concentration of A minus. All right, now this is a pretty useful expression. However, we don't often, even though we kind of want the concentration of hydronium ion at equilibrium, it's more important to express the pH, right? Because pH is something measurable. So I'm going to take the negative log of everything. So and I'm going to do this. All right. Now we can do some rearrangement here. So this is going to be negative log of Ka plus the negative log of concentration of Ha over A minus. Okay, so that's a log identity. If you multiply two things within the log, it's the same as taking the log of the first thing plus the log of the second thing. Now this negative log Ka, we call this pKa. And so that would be minus log of concentration of Ha over concentration of A minus. Now, for some reason, somebody determined that instead of expressing it this way, they wanted to get rid of this subtraction. So there's another log identity where if you have a ratio, if you're taking the log of a ratio like this, if you flip the ratio, it changes the sign in front of the log. So that's going to be pH equals pKa plus log concentration of A minus over concentration of Ha. And we'll write this as a generic form as pH equals pKa plus log log of concentration of base over concentration of acid. And this is the Henderson Hasselbalch equation. And it is tremendously useful for buffered solutions. Okay, now if I have a base, so I have a base plus water, there has to be a base equivalent, right? OH minus plus HB plus. So Kb equals concentration of OH minus times concentration HB plus over concentration of B. So I can go through the similar steps and I can get POH equals pKb plus the log of acid over base. Okay, so this would be the base version of the Henderson Hasselbalch. And you notice they're very similar, but in the sort of acid version with pH, the base goes on top. And in the base version where we find POH, the acid goes on top. Just something to keep in mind. Okay. Now the final thing that we're going to need here is we're going to go back to when we talked about Ka times Kb equals Kw. Okay. And I'm going to take the negative log of both sides. So negative log of Ka times Kb equals negative log of Kw. All right, so negative log of Ka plus the negative log of Kb equals the negative log of Kw. So this is pKa plus pKb equals negative log of Kw, and Kw is 1 times 10 to the minus 14, so that's just a constant of 14. So this is another thing that as we're approaching these, we might need. All right, so let's take a look through our reactions, the stuff that we did yesterday and the day before, and see how Henderson Hasselbalch might help us. Okay, so here we go. We did this equation. Now Henderson Hasselbalch actually isn't going to be a ton of help here because in order to use Henderson Hasselbalch, we need these values. We need these equilibrium values. And we have this one simplified to 1.0, which would be useful, except for these are both x's, so we don't actually know those. So we have to solve them sort of the more traditional way. Okay, now what about this one? Well, this is a buffered solution, okay? And buffered solutions are great for Henderson Hasselbalch. So I can take pH equals pKa plus the log of the concentration of base over the concentration of acid. All right, and that gets us negative log Ka plus the log of the base, which in this case is going to be F minus, over the concentration of the acid, which is going to be HF. And then I can plug some numbers in. So negative log of 7.2 times 10 to the minus 4 plus the log of 1.0 over 1.0. So the concentration of both of these things at equilibrium is 1, and 1.1 divided by 1 is 1, log of 1 is 0. So we just end up with pH is negative log of 7.2 times 10 to the negative 4, which is 3.14, which you'll notice is what we got here. I skipped a couple steps here to make this calculation actually go a little faster in the last video. But if you don't skip that calculation, then this becomes a lot easier. And actually, it allows us to almost do this without a rice table. Like, we know it's probably good to write a rice table just so that we can establish that these equilibrium values are not gonna change, and that we're gonna use our assumption that these values are basically 1. And then we can go and plug into Henderson Hasselbalch. All right. So still, I mean, it's still a lot of work, right? Like Henderson Hasselbalch hasn't changed too much. So let's take a look. No help in the top one, but in this one, also really no help because this initial value for the concentration of fluoride ion is so small that this x value is probably going to end up affecting that. So we can't actually use Henderson Hasselbalch here. We have to go through and at least solve this part um, before we solve more stuff. Now, once we have our value of x, we could use Henderson Hasselbalch to get the pH rather than, but at that point we have pH equals negative log concentration of hydronium ion, which we just solved for. So that would probably actually be easier. But this one, our final one, when we have a buffered solution at equilibrium and we disrupt it, this is a good scenario for Henderson Hasselbalch because basically, once I do this part here, once I do this first part where I establish what's going to be left after that initial reaction happens, then I can take those values and I can plug them straight into Henderson Hasselbalch. Because look, the whole point of a buffered solution is that our concentrations are going to be really high. So once I see this and I know I do need to convert them to concentrations. But for this one, it was really easy. Everything was 1 liter. But this would be a good opportunity for a Henderson Hasselbalch. Now, I'm going to do something a little silly here just to kind of show what we would do. So the concentration of base would be the 1.05 moles of base over 1 liter. And the concentration of HF would be 0.95 moles over 1 liter. Okay, so now this is how I would fully show my work, where I'm converting each one of these to a concentration before I do my math. Okay, and when I do that, I get 3.19. Okay, so look, there's 3.19. Here's also 3.19. Now, again, I simplified this step here, and there was a lot of work that I didn't show that went into that to get from this point here, to get from this line to this pH. Okay, whereas I can take this line here, plug it in to Henderson Hasselbalch, and get a concentrate or a pH, and that is really much faster than doing another rice table and a bunch of stuff after that. So that's Henderson Hasselbalch. It can simplify buffer problems quite a lot.